When you draw an L and mark the line going down, Y, and the line going from right to left, X, you get a graph. Graphs let us compare two things. For example, the numbers of tacos I ate over time. A graph creates a shape, and that shape has a trend line. That trend line has a data fingerprint.
There are two kinds of fingerprints in this world. Ones that are shaped like a perfect bell, smooth, symmetrical, and beautiful. We call these parametric fingerprints. And the ones that are not shaped like a bell, lumpy, skewed, lopsided, unusual, they call these non-parametric fingerprints. Most real-world data is non-parametric. Human behavior is messy.
Now imagine a crime scene. Data fingerprints everywhere, all over the walls, all over the floor. The question is, which fingerprint belongs to who? That's where Kruskal Wallis comes in.
Okay, the data mole and Freddy Python gave us a great foundation. Parametric fingerprints and non-parametric fingerprints. Let's make sure everyone is fully locked on to what that means before we go further.
The bell one is a pretty one, right?
Exactly. The bell curve, or parametric fingerprint, is what you get when data is perfectly balanced. Most values cluster in the middle, and it falls evenly off on both sides. Think of it like that. The height of every person in the city. Most people are around average height, and very few are very tall, and few are very short. A perfect bell. Parametric tests, like the t-test or ANOVA, they assume your data is a bell. They are built around that assumption. If your data isn't a bell and you use those tests anyway, your results are going to be wrong. You need a different tool. That tool works on any shape and is called Kruskal Wallis. And the statisticians Kruskal and Wallis looked around at real-world data, agricultural yields, medical measurements, and economic data and said, this data isn't a bell. This data is lumpy and skewed and weird, and we can't just throw ANOVA at it and pretend everything is just fine.
How does it work?
The ranking part is my favorite part because this is where it gets elegant. Okay, imagine we had three groups. Group A, B, and C. For example, or my personal favorite, tacos consumed amongst 3 different time zones.
Get a taco one.
So 3 friends, Panda 1 eats 2, 5, 7, and 12 tacos over 4 weeks. Panda 2 eats 1, 3, 4, and 9. And Datamol eats 6, 8, 10, and 11.
Datamol eats a lot of taco. Datamol's gotta eat!
Now, in a normal test, we'd compare the actual numbers. But Kruskal Wallis doesn't care about actual numbers. It throws them all into one big pile, all 12 values from all 3 groups, and ranks them from smallest to largest. So we rank all values together. 1 gets the rank of 1, 2 gets the rank of 2, 3 the rank of 3, all the way up to 12 getting the rank of 12. And then we put each value back into its original group, but now labeled with its rank instead of the original number.
Wait, so it doesn't matter anymore if the numbers are big or teeny? Exactly! A value of 1 million and a value of 1,000, if they're next to each other in ranking, they're just rank 47 and rank 48. The distance between them stops mattering. Only their order matters. That's like when teachers said it doesn't matter if you get 95 or 100, you both get an A. That's it. Shockingly close to correct.
Then the test asks if the ranks are evenly spread across all the groups. Or are the high ranks all bunched up into one group and the low ranks all bunched up into another group? If the ranks are evenly spread, the groups look the same. But if one group has it almost all high ranks, then something is different about that group. Okay, the test runs, the ranks are calculated, the H statistic is produced, and then it all comes down to one number, the p-value. This is the number that gives you the answer.
What the answer to what?
The answer to, are these groups the same or different?
How did that number tell you that?
Here's the rule, and this rule never changes. The p-value is basically the probability that what you're seeing is happening by pure random chance. If there's a 50% chance it's random, you can't claim the groups are different. If there's only a 2% chance it's random, then something real is going on.
Where did the 5% come from? Why not 0.1 or 0.01?
That's another great history question. That threshold, 5%, was set by the same Ronald Fisher who invented ANOVA back in the 1920s. He essentially said, if there's less than 1 in 20 chance that this is random noise, we call this a real finding. The field of statistics adopted it and it stuck. Before we go any further, we need to talk about something. The null hypothesis.
The what?
Every statistical test starts with an assumption of innocence, if you will. In Kruskal Wallis, the null hypothesis is all groups being compared are drawn from the same distribution. They are identical, there is no difference. That is literally like saying before we look at any evidence, we assume everyone's fingerprints are the same. Precisely. The test does not try to prove they are different. It tries to find enough evidence to reject the idea that they are the same. Like a trial, the defendant is innocent until evidence says otherwise.
So the test is like a judge?
The test is like a judge. The p-value is the verdict, and if the p is above 0.05, not enough evidence, the null hypothesis stands. Fingerprints are considered the same. If p is below 0.05, evidence is too strong, we reject the null, fingerprints are different.
And if somebody's fingerprints show up at the crime scene and they match, that means they were there?
Now you understand why this matters. Alright, let's talk about when this tool belongs in your toolkit, because Kruskal Wallis is powerful, but it's not for every situation. Use it when you've got 2 or more groups that you want to compare, and your data is non-parametric, meaning it failed the normality test Shapiro-Wilk, or you can visually see that it isn't a bell.
You use it when you want to know if these groups are from the same population, or if they're fundamentally different. Can you use it on anything?
Almost. It works on ordinal data like survey rankings from 1 to 5. It works on continuous data that isn't normal, and it works on skewed data. It works even when sample sizes are unequal across groups. The most important relative is the Mann Witney U test, also known as the Wilcoxon Rank sum test. This is Kruskal Wallis's little sibling. It does the exact same thing, but for exactly 2 groups instead of 3 or more. So, if you've got 2 groups, use Mann Witney U. If you have 3 or more groups, use Kruskal Wallis. The math comes out the same, but Mann Witney U is the proper tool for 2 groups.
Remember, every data set leaves a fingerprint, and now you know how to read them, and that's called value. And because of that, thumbs up, subscribe, smash bell, and answer in the comments below what statistics you want to learn about next. But first, check out this video up here. Bye!
Big data.